Hello and welcome to another video. In this problem, we're going to be working on the third problem from the contest 373 that was on Saturday, and it's going to be make lexicographically smallest array by swapping elements. And so you're given a zero index array of positive integers nums and a positive integer limit. In one operation, you can choose any two indices and swap the numbers if the absolute value difference is less than the limit or equal to. Return the lexicographically smallest array that can be obtained by performing any operation any number of times. Lexicographically smaller just means kind of like a string, where if you can have a 1 in front of a 5, it is smaller and so on. So essentially something like 15398 would be smaller than 51398. So if you can treat these as letters and make a word, that's like an easy way to explain it. Like A would be A, or 1 would be A, 5 would be E, I think, and so on. Make a word, and what's like the smallest word, or not the smallest word, what's the word that comes first alphabetically. So essentially you want the smallest numbers possible in the beginning. And also for something lexicographically, notice that like if this is a 1 and whatever, that is automatically smaller than 2 and whatever, right? So even these elements can be really big. It can be like 199999 is smaller than like this. So if there's a difference in one element, the first difference is the one that matters. And also the constraints are 10 to the fifth, so you're looking for like an n log n or an O of n solution. So ideally, once again, look for like a 2-pointer or something like that. And let's go through these examples. So in the first example, what you want to do is you can swap the 1 with the 3 because they are small enough. Actually, you don't want to swap, sorry. You don't want to swap the 1 with the 3. You want to swap the 3 with a 5 because they are close enough. And then you want to swap the 8 with a 9, so you would get 13589. In the second example, so we can swap these two, and then we can swap these two as well. And in the third example, looks like we can't swap anything because everything's too far apart. So the thing is, you might think like, let's just take numbers and let's see if there's anything within the limit or something, and let's swap it, but it's kind of tricky to do that because you might have to have multiple swaps. So let's say we have like limit 2, and let's say our numbers are like 8. Or actually, let's say our limit's 1. This will make it easier. So our limit's 1, and our numbers are like 8, 9, and then we have like 5, 6, 7 or something. Or actually, let's do it the other way, right? 8, 9, 7, 6, 5. So in the beginning, you can't just swap. You can't just be like, what's the farthest thing? Like, what's the smallest thing within the limit I can swap it with, which would be 7? Because you might have to do multiple swaps, right? Like, when we swap here, so we do want to swap the 8 and the 7. And if we do that, then we will get 7, 9, 8, 6, 5. But then we want to do more swaps now, right? Because now the 7 allows us to swap us with the 6, where the 8 didn't let us do this. Now we do want to swap again. So we'd have a 6 here and a 7 here. We can just do that in place. 6, 7, and then we'd want to swap again. So you see how like every new swap lets us swap new elements that we weren't able to do that before. So you can't just like greedily say, let me just take the biggest thing or something. Same thing here, right? You could swap the 9 with the 8, and then with the 7, and then with the 6, and so on. So at the end, you would get 5, 6, 7, 8, 9, but there's going to be a ton of swaps. So it's not the best way of doing it, and this is going to be like something like an n-squared solution, roughly. So the better way of doing this is, and remember, we need an O of n solution. Or, yeah, we need O of n and log n. The better way of doing this is actually, we can group this into chunks. And for a chunk, we know everything in the chunk is swappable. So let's say we have 5 numbers, like A, B, C, D, E, and they are increasing. And they are all, the difference is all between limit, right? So like the difference between all of them is limit or less. So like B is like A plus 1, C is B plus 1, let's say, D is, so on, right? Like a similar way of doing that would just be like 1, 2, 3, 4, 5. So these are all within the limit. So if we have that, if we have 5 numbers that are all within the limit, increasing, then any one of these can be swapped for either one. It would just take multiple swaps, right? So like 1 could be swapped with 5 because we'd swap 1 with 2, then we'd swap 2 with 3, then 3 with 4, then 4 with 5. So if we actually group our numbers into chunks in increasing order, and we just know like we can get from one of these to any other ones, then we can swap them. So you can do something like a union find, but there's something even easier. And so what we're actually going to do is this is going to be a two-step process. And let's just go through this array, how this is going to work. So first, we want to sort these, right, in increasing order so we can get these chunks. And the chunks is going to be very easy to get because, like, let's say these were sorted in increasing order. Let's say, obviously, this is all one chunk. But let's say our numbers had like a, let's actually add a few numbers. Let's add like 1, 2 in here. So now if we sort it, it would be like 1, 2, 5, 6, 7, 8, 9. So we can easily figure out like where the chunks are once we have a sorted array, because we could be like, okay, well, you can go from 1 to 2, so that those are in the chunk. But then you can't go from 2 to 5, so this is the separator, right? So this is a separate chunk, and then we can go from here to here to here to here to here. So if we know that we can go from 1 to 2, then obviously anything in the chunk of 1 to 2, right? Like we can just figure out where the indices of this. So let's write this one more time actually. So 1, 2, 5, 6, 7, 8, 9. So we would know that everything in this chunk, the order we would want at the end is increasing order, right? We'd want it 1, 2. Because let's say this was the other way. Let's say this was like this, 2, 1. Let's even move some numbers around. So let's move this over here just to make it kind of more interesting. So let's say 2, 1, 6. We can even, yeah, sure, this is fine. So sorted, it would be the same thing. So now everything that's in this chunk, what we want to do is we want to have every chunk basically end up being in a sorted order, right? So where's the 1 and the 2? It's here. And so at the end, we would want to swap these. And everything in this chunk, right? So this number, this number, this number, this number, this number, we know that we can get from one of these numbers to any other one, right? Because they're all within limit. So we want this whole chunk to be in sorted order. So at the end, our array should look like 5, 6, 7, because that's part of this chunk. Then we'd have this 1, 2 in sorted order. So we'd have 1, and then we'd have 8, 2, 9. I believe this is correct. Right. So this chunk here is now in sorted order, which is this chunk here, same indices. And 1, 2 is also the second chunk, and that's in sorted order, right? We can even draw that in another color. And that's essentially what our problem boils down to, is figure out the chunks by just sorting the array. And then all we need to do, like, let's actually go back and figure out how we would put this where it needs to go. So what we're going to do is we are going to, let's get rid of these arrows, and I'll show what we're going to do. So, and these are the chunks, but let's get rid of all this. Let's go back to an original result. What we're going to first do is just initialize an empty array with this amount of indices. So we're just going to write down the indices here. So we can initialize every value to 0. So this is 1 to 6, right? Or 0 to 6. So we're just going to draw the indices here. We're going to say every value here is equal to 0. I'm not going to draw those, but we can just write that. Actually, I guess I can. So we'll have 7 zeros. So 1, 2, 3, 4, 5, 6, 7. And these are the indices, right? We're just making a new array that's the same length as this original array. And for this array, we're going to add the index into each element here. So actually, we're going to create a new array that will just have every element here and its index. So it'll look like this. So it'll look like 8, 0, 9, 1, 7, 2, and so on and so on, right? So every single element here will just have its index. We can index this as well. So like this. Then what we're actually going to do is we're going to sort this array that we make. So let's write down the sorted array over here. So the first element will be 1, and it will be at index 5, right? And the reason we want the index is we want to know, like, where was it originally? So 1 at index 5, 2 at index 3, 5 at index 4, 6 at index 6, 7 at index 2. Yeah. And let's have some more space. 8 at index 0. And 9 at index 1. So now this is pretty easy to do, right? You can just make a new array with all of these and its index. So you can just like enumerate it or something and get all the numbers in its index and then sort by the actual number. So now we have a sorted array where it's sorted by the number increasing, and we also, for every number, have its original index. So now what we are going to do is we are going to traverse this, and we're going to look for chunks. And for everything that's in a chunk, so first we're going to write down like where is the index of the first element in our chunk. So that'll be here. And then as we traverse, we will actually take all of these indices and we'll put those into an array. So we will traverse, we'll say like, okay, this is like a chunk. So we'll put the index into an array. Then we'll go over here and we'll say, is this a new chunk or is this the old chunk? It's the old chunk, right? Because you can go from here to here because they're within limit, because limit is 1. So we will add this index into the array. So essentially we'll have an array of indices. And then once we get to a new chunk, we'll just say, okay, well, we know where our previous chunk started. It started over here. And we know the indices. So what we want is we want to sort the indices because we want, remember, in our chunk, in the output, we want the chunk to be in sorted order, right? So the chunk is at index 5 and index 3. It's these two, right? These two. These two should be, to make the smallest lexicographical string, should be 1 and then 2, right? So what we're going to do is we're going to sort this array. So we sort it here after because this is a new chunk, right? So we have our whole chunk. We sort it. And then we just say, okay, well, let's just start at the start of the chunk and let's put these numbers in where they should go. So 1 should go at index 3. So we'll do that. And 2 should go at index 5. So we just traverse the chunk that we found, which is this chunk here. Or sorry, 3 should go at index 5. Now, and we do that every time we encounter a new chunk, right? So here, this is a new chunk. So once we encounter this chunk, we will take our array of indices and sort it and do this. Then, now that we found a new chunk, so let's maybe draw this chunk in another color. Let's say this chunk is green. Then once we did all that, we're going to take our array of indices and clear it out. So it's going to be empty again because we have a new chunk. So completely empty array. Now same thing, we're going to traverse until we find the new chunk. And we're just going to keep adding indices to this array of indices. So we have a 4. Then we go over here. Is this part of the same chunk? Yes, it is, because we can go from 5 to 6. So we'll add 6. Is this part of the same chunk? Yes, it is. So we'll add 2. Same chunk. 8, or not 8, 0. And same chunk. And once you're actually done with this loop, you will have to like do this one more time, right? Because essentially you'll have a chunk. So now that we're done, like we do this thing every time we find a new chunk, and at the very end of the loop, we're gonna have to do it one more time because we have this chunk left over. So we have this chunk left over, and we have all of the indices where these elements should go. So sort them again. Get 0, 1, 2, 4, 6. And where was the start of our chunk? It was right over here. We can just record that every time we get a new chunk, record the start. And now the same thing, we just traverse the elements and we just put the elements in the correct index. And we just traverse the elements and we go to the index. So we just go like 5 goes here, 6 goes here, and so on, right? We can just traverse both of these arrays and they're going to be the same length. So 5 is going to go at index 0. So let's empty these out for the new elements. So 5 is going to go at index 0. 6 is going to go at index 1. So 6. 7 is going to go at index 2. 7. And then 8 goes at index 4. And 9 goes at index 6. And there we go. Now we have this lexicographically smallest array because every chunk is basically completely increasing, right? Like this is one chunk. And this is the other chunk. So this would be our answer. And that's pretty much all we have to do this problem. So just to remind us again, what we need to do is we need to include an index with all of these, then sort them, and then every new chunk we find, keep track of where the chunk started and keep track of all of the indices that were in this chunk, sort the indices, and then you basically say, okay, let's take the smallest number and put it in the first available index. Let's take the second number and put it in the second available index, and so on. So then our chunks, if you look at our chunks separately, they're all sorted, and that's going to lead us to the lexicographically smallest array. And yeah, that's kind of it. So definitely significantly harder than the previous problems in the contest, but doable. So yeah. So let's code it up now. And first thing we're going to do is we need to make this array, right, with the num and its index, and we also need to sort it by the number. So we can do that. So we're going to say nums with indices equals, we're going to have this sorted, And the array is going to be like this, right? So we're going to have num I. Let's actually do, yeah, let's do it another way. So we're gonna make a list comprehension here. So what we want is we want every single, so we can say we can have a tuple here. So we can have like nums I, and then we can have the actual index for I in range length nums, right? So take nums, get the number and its index and put it into a tuple and sort by the actual number. So now that we have that, we're also going to make a new result array. So we'll just say this, initialize it all to 0. Now what we need to do is we need to actually record, like we're going to check, is our current index bigger, or not our current index, is our current number bigger than our last number? Because we need to find the new chunk. So we're going to initialize our last number to just be the first number in nums, because we need some kind of default value so we don't, like, when we're at the first value, there is no previous. So we're going to initialize it previous to this thing here at index 0. And remember, this is a array of tuples, and the thing at the first index is the number, and the second thing is the index, so we want the number. So we also need to record the first item in each chunk, so then we can traverse, right? So we're going to do that. So we're going to say like first equals, and we'll set it equal to index 0 for now. And we also need our array of indices that we're going to be sorting every time we have a chunk. So then we can have for num index in nums with indices. We basically need to check, is this number compared to the previous number greater than the limit? And if it is, then we have a new chunk. So that's what we need to do. So we're going to say if num minus previous is greater than the limit, then we have a new chunk. So this is where we would handle that. So what we want to do is we want to actually sort our indices, right? So we could say for index in sorted indices, or you could sort it beforehand, either one's fine. Now we need to actually write the number in the right place. And remember, where are we writing to? So first is going to be the start of the chunk. So we're going to write whatever the number was that was first, and then we're just going to keep incrementing first to go through the chunk. So first we'll start at the start of the chunk, and then we will iterate through first. Like we'll keep increasing first, and we'll also keep going through the indices. And so at the very end, first will be at the start of the new chunk. So if we had like 1, 2, 3, and then we have this other chunk like 8, 9, essentially first we'll start here, and then it will go here, and then finally it will end up here, and this will be the start of the new chunk. So what we need to do here is we need to say result at index equals nums with indices first, or cur, or whatever value you want to use. And then remember, we want the value here, right? So we want the value here, and then we want to increase first. There's probably like other ways to do it. This is just how I did it, as long as you just keep track of your chunks. And once you're done with all of this, once we actually took our entire chunk and we put it into our result, now remember we need to empty out our indices array because we're going to use it for the next chunk. So we'll say indices equals new array. And regardless, previous is going to be the number, right? If you use the chunk or not, previous is going to be the new number now. So previous is going to be num, regardless of if you have a new chunk or not. And what you want to do now, also regardless of if it's a new chunk or not, you want to take your current index, and then you want to actually append it to your indices, right? So we'll say indices, append the current index. Okay. And remember that once we're done with this loop, we actually have to do this one more time, because we're going to have a chunk left over that once we're done iterating through these, we'll still have a chunk left over. So we basically have to take this code and copy it one more time, because we will have that chunk left over. And finally, we just need to return result. And let's take a look. And there we go. Okay, so you see we have a pretty efficient solution. And we were able to do it. And so let's talk about the time. So essentially what we're doing is, first of all, we sort this array, which is n log n. Then essentially what we're doing is we're taking chunks and sorting them. So every chunk will be like I log I or something, right? Where all of these i's together add up to n. So if you add all these up together, then this is going to basically be big O of n log n. Because if you sort smaller sections and you, like, if you take an array of like 1,000,000 and you sort 10, segments of length 10, it's going to be faster sorting individual segments because you're going through a shorter array. So, right? So let's say your array was 1,000,000 and you're sorting segments of length 10, then it would be like 10 log 10 times 1,000,000 over 10. So this would basically end up being 1,000,000. Make sure I get the right amount of zeros this time. It'd be 1,000,000 log 10 instead of 1,000,000 log 1,000,000. So it ends up being big O of this. And yeah, so that's just going to be n log n here. And for space, so we did make this nums with indices, which is O of n. We also made this indices, which is also O of n, because technically everything can be one full chunk, right? So if everything was one full chunk, indices would fill up all the way. And regardless, this is the upper bound of the space complexity anyway, because we're making a new array. You could do this in place if you want to. It would save you space, but it's generally bad practice, so I didn't. And yeah, I think it's going to be all for this one. So now just the hard problem left. And yeah, I'm not sure if I'll make a video for it. Hopefully I will. Some of these hard problems for the contest are like significantly harder than LeetCode hards. So I'll see how it is, and we'll see if I do that one. But hopefully you enjoyed this one. This one should definitely be doable. The hard problems, depends on the problem. Like I said, some of them are like our LeetCode hard. Some of them are like 3 LeetCode hards. So we'll see how that goes. But yeah, if you enjoyed this one, then please like the video and please subscribe to the channel. And I'll see you in the next one. Thanks for watching.